Hello everyone! In this series of videos, we will discuss solving systems of linear equations. Systems of linear equations are the most fundamental objects in linear algebra. In this first part, we will review some basic definitions and concepts about linear equations and systems of linear equations. So let's recall from high school algebra that a linear equation in two variables, x, y, is an equation of the shape a1x plus a2y equals b, where a1, a2, and b are constants. From elementary calculus, we learned that the equation of a plane in three-dimensional space has the form a1x plus a2y plus a3z equals b, where a1, a2, a3, and b are constants. This is called a linear equation in three variables x, y, z. In general, a linear equation in n variables, say x1, x2 up to xn, has the form shown below. Here, the numbers a1, a2 up to an are called the coefficients of the equation, while b is called the constant. By a solution of a linear equation, we mean an n-tuple, say s1, s2 up to sn, such that the equation is satisfied if we plug in s1 for x1, s2 for x2, and so on up to sn for xn. The set of all solutions of a linear equation is called the solution set of the equation. The solution set of a linear equation with two variables or three variables can be visualized using the graph of the equation. So here we see the solution set of the linear equation x minus y equals negative 1. We see that the solution set is a line in the Cartesian plane. For an equation with three variables, the solution set is a plane in the three-dimensional coordinate space. A system of m linear equations in n variables is a set of m equations, each of which is linear in the same n variables. So if x1, x2 up to xn are the variables, then such a system has this form. Here, aij denotes the coefficient of xj in the ith equation. So for instance, a32 is the coefficient of x sub 2 in the third equation. A solution of a system of m linear equations in n variables is an n-tuple, say s1, s2 up to sn, that is a solution of each of the equation in the system. Let's consider some examples. So here we have the system as shown. This system has a solution given by x equals 1, y equals 2. The solution is obtained by adding the two equations to obtain 2x equals 2, which gives x equals 1. And then substituting this value to the first row, we see that y equals 2. The graph of the system is represented by two intersecting lines, as shown, and the solution set contains the point of intersection here. Next, consider this system. This has a solution given by x equals 3, y equals 0, as you may check. But in fact, this system has infinitely many solutions. The solution set consists of ordered pairs xy with parametric representation given by x equals 3 minus t and y equals t. This is because, as we can observe, the second equation can be obtained from the first equation by multiplying both sides of this equation by 2. Consequently, the graph of the first equation and the second equation are the same. And so the graph of the system is represented by two lines that coincide. The system x plus y equals 3, x plus y equals 1 has no solution because it is impossible for the sum of two numbers to be equal to 3 and 1 simultaneously. Indeed, if you sketch the graph of these two equations, you will obtain two parallel lines. A system of linear equations may or may not have a solution. If it has a solution, we call it consistent. Otherwise, we call it inconsistent. In general, for a system of linear equations in n variables, we only have three possibilities for the solution set. Either the solution set has exactly one element, there could be infinitely many elements in the solution set, or the solution set is empty. A common approach for solving a linear system is by repeatedly eliminating variables and performing back substitution. This method involves a chain of equivalent systems, meaning systems with the same solution set, each of which is obtained by applying one of the following three operations: interchanging two equations, multiplying an equation by a non-zero constant, and adding a multiple of an equation to another equation. To illustrate, let's consider this system S. We have a system with three equations and three variables x, y, z. There are several ways to begin, but we would like to use a systematic procedure that can be applied to large systems. The first step is to make sure that in the first equation, the coefficient of the first variable is equal to 1. So in our case, we are done. Otherwise, we interchange the first equation with a suitable equation. Now we use the first equation to eliminate the x's from the other equations. So for instance, to eliminate x in the second equation, we add the first equation to the second equation. That will result to a new second equation given by y plus 3z equals 5. So observe that x is gone in this equation. We do the same thing with the third equation. So we eliminate this x here. That is obtained by multiplying negative 2 to the first equation, then adding the result to the third equation. That process will give a new third equation given by negative y minus z equals negative 1. And then we repeat the process. So next, we make sure in the second equation that the second variable has coefficient 1. So far, we're okay here. Then we use that to eliminate the second variable in the third equation. So in this case, we can do that by adding this second equation and the third equation. So this will produce the new third equation, 2z equals 4. So we already eliminated y in the third equation. But note that the third equation can be simplified as z equals 2 by multiplying both sides by 1/2. At this point, we can either proceed with back substitution or continue applying any of the three operations described above. In other words, you may eliminate z in the second equation using the third equation and eliminate the z in the first equation using the third one, and then eliminate y in the first equation using the second one. But let us finish this with back substitution. From the third equation, which is z equals 2, we can compute y from the second equation. We have y equals -1. And finally, using the values obtained for y and z, we can use the first equation to obtain the value for x. This shows that the system S has a unique solution given by x equals 1, y equals -1, and z equals 2. Let's consider another system. So, applying the same idea, so we make sure that in the first equation, the first variable, x1 in this case, has coefficient 1. So, okay. Then we use this equation to eliminate x1 in the second and third equations. So, to eliminate x1 in the second equation, we multiply -2 to the first equation and add it to the second equation. That will produce 5x2 minus 4x3 equals 0 as the new second equation. We do the same to eliminate x1 in the third equation. So we multiply -1 to the first equation and add the result to the third equation, and this will produce this new third equation, 5x2 minus 4x3 equals -2. Now, note that we can eliminate the second and third variables from the third equation using the second equation. We multiply -1 to the second equation and add it to the third equation to obtain this equation. But this equation 0 equals -2 is clearly absurd. And this means that the system S has no solution. A third example, consider the system S as shown with 3 equations and 4 variables. Again, we are done with the first equation. The first variable has coefficient 1, and we use that to eliminate x1 in the second and third equations. So, multiplying -2 to the first equation and adding the result to the second equation, we get this new second equation. And multiplying -3 to the first equation and adding the result to the third equation, we get this new third equation. Now, observe that if we multiply -2 to the second equation and add the result to the third equation, we get a new third equation given by 0 equals 0, which does not give us a new information. So we can simply get rid of this equation and just write the system as a system with 2 equations. Note that this system is equivalent or still equivalent to our system S. If we put x2 equals 0 and x4 equals 0, then we obtain a solution given by x1 equals -9, x2 equals 0, x3 equals -7, x4 equals 0. But in fact, there are other solutions. For instance, x1 equals 1, x2 equals 0, x3 equals 0, x4 equals 1 is also a solution, as you can check. In general, the solution set of this system S is given by the following set. So it's the set of all 4 tuples which are parameterized by S and T, or the second variable and the fourth variable.